Hello guys, in this video we are going to be looking at problems on applications of dimensional analysis. We have discussed the applications of dimensional analysis and want to use that to solve some questions under dimensional analysis. The first question here says that the heat capacity C of a solid can be expressed as a function of temperature T. To fit the expression, C is equal to alpha T plus beta T cube. Find the possible units of alpha and beta. Let's look at it. The equation is C equals to alpha T plus beta T cube. Now, to solve this, we are going to be making use of principle of dimensional homogeneity, which says that if we have a mathematical expression of x plus y is equals to z, this equation will be dimensionally homogeneous if the dimension and unit of x is the same as dimension and unit of y and is same as dimension and unit of z. That means if they have the same unit and dimensions, then we can say that equation is dimensionally correct. Another example, if we have A equals to C plus D plus E, this equation is going to be dimensionally correct if all the terms have the same unit and the same dimensions. That is, the dimension and unit of A is the same as dimension and unit of C, same as dimension and unit of D, the same as dimension and unit of E, and we say that the equation is dimensionally homogeneous or consistent. Now, with this principle, we can use it to solve this question, meaning that if this equation is dimensionally correct, that is to tell us that the dimension of C is the same as dimension and unit of alpha T and is the same as the dimension and unit of beta T cube. That is, the dimension of C is the same as dimension of alpha T. The dimension of C is the same of unit of beta T cube. And dimension of beta T cube is the same as that of alpha T. That means all the three parameters, they are having the same unit and dimensions. As a result of that, we can do it this way by saying C is equals to alpha T. Let's take this as equation 1. Then the second one says that C is equals to beta T cube. Why is it so? Because I've already said that we are applying principle of dimensional homogeneity, which makes us to equate this parameter C to be equals to alpha T. At the same time, this parameter T, which is the variable C, is the same as that of beta T cube. Now, they ask us to solve for the unit of alpha. Starting by looking at this, let's get the unit of C and the unit of temperature. C is known as heat capacity, and we have defined heat capacity as the quantity of heat energy per unit temperature. If that be the case, let's get the unit. The unit of heat energy is joule, while the unit of temperature is Kelvin or degrees Celsius. In that case, we can write it as joule per Kelvin. This is the unit of heat capacity. Now, what is the unit of temperature? The unit of temperature is Kelvin. We know that. Now, let's try to use equation 1. We are going to be using the subtopic we have considered that says that we can use dimension analysis to get the unit and dimension of constant. Now, the constant involved is our alpha. The constant is our alpha. Since alpha is our constant, we can make alpha the subject of the formula from equation 1 by writing it as alpha is equals to C over temperature. That makes it equation 3. Now that I've gotten the equation for alpha, we can substitute it into alpha is equals to the unit of its capacity. Sorry, that's temperature. Unit of its capacity is joule per Kelvin, while the unit for temperature is Kelvin. In that case, if we try to simplify this, alpha is going to give us joule per Kelvin is per minus 2. This is the unit for alpha. Now let's look at the unit of beta. In this case, we also need to make beta the subject of the formula by dividing both sides by t raised power 3, means beta is going to be equals to c over t raised power 3. That makes it equation 4. Therefore, we can say that beta is equals to the unit of its capacity is joule per Kelvin, while the unit of temperature is Kelvin. In that case, we have it raised power 3. So to simplify this, we are going to write it as beta is equals to joule per Kelvin raised power 4. Minus 4 rather, Kelvin raised power minus 4. Pardon? So this is the unit for beta as joule per Kelvin raised power 4, while the alpha is joule K raised power minus 2. That is all about this question. Now let's look at the second example. So in this second example, it says determine if the formula T is equals to 2 pi square root of m over f over x is dimensionally correct, where T is the time period, m is mass, f is force, and x is distance. How do we go about this? There are two approaches we can use. We can either work with the square root or we ignore the square root. Remove it. How do we remove the square root? By finding square of both sides. That will be easier to do. So let's find square of both sides. That gives us t square is equals to 2 pi all square root of m over f over x. In this way, we are going to be having t square equals to 4 pi square. We are left with m over f over x, because 2 pi all square simply means 2 pi times 2 pi, and that will give us 2 times 2 will give us 4. 1 pi times pi will give us pi square. So in that case, this x that is here will go up. Then we can write it as t square is equals to 4 pi square mx over f. This is our new equation. Since I decided not to work with the square root, you can as well work with the square root by not introducing square to both sides. Now, to solve this question, since the question did not specify whether we should use dimension method or base unit method, we can use any of the two. So I want to use dimension method to solve this. So that means I need to solve for the dimension of period. The dimension of period is capital letter T, while the dimension of mass is n. Dimension of distance is L, and dimension of force, we have discussed that it is mLT raised power minus 2. Now that we have gotten the dimensions of the variables involved, then we can return it back into equation 2. That means anywhere we see the time period, put t, and that is square, is equals to 4 pi square is a pure number, so it doesn't involve our dimensional analysis. Numbers don't have dimension. So in that case, we are going to ignore it. Then what is dimension of mass? That is capital letter M. Dimension of x is L over dimension of force is mLT raised power minus 2. In this way, we can simplify by using the knowledge of indices, where the mass cancels each other, then L cancel L. So in the long run, we are going to be left with t square equals to 1 over t square. And if we simplify this, we are going to be having t square equals to t square. Now, since we have the same parameters, we have the same dimension on both sides, as the left-hand side and the right-hand side, yes, we can say that the equation is dimensionally correct. Therefore, the principle of dimensional homogeneity is obeyed in this equation. Let's move to the third example. Here, the question says a radio signal of length L emits signal of wavelength lambda. Wavelength lambda and power P. These equations are related by sorry, these quantities are related by P equals to Ki square L over lambda everything all square, where I is the current. Determine the SI unit, if any, of the constant K. How are we going to go about this? Solution. We have to write the equation P is equals to Ki square. They'll be having L over lambda square. So open this bracket by writing P equals to Ki square L square over lambda square. That is equation 1. So it's equation 1 as well. Now the next thing is that we are going to be using the principle of dimensional homogeneity that says that if the equation is dimensionally correct, that means whatever we have on the left hand side is the same as what we have on the right hand side. Now we are going to be using the second application of dimensional analysis that we have discussed in the previous video, that says that determination of units and dimensions of constant. So there's a constant here which is K, and if you remember, we said that whenever we want to determine the units and dimension of the constant, we have to make the constant the subject of the formula. So let's make K the subject of the formula by saying P lambda square is equals to Ki square L square. Now on this side we still have our values attached to K, which are current and length. So we divide both sides. So our K becomes P lambda square over I square and L square. This is our new equation, equation 2. So we should determine the units of K, which is the constant. The unit of power is watts, while the unit of wavelength is meter. Then the unit of current is ampere, and the unit of length is also meter. We can substitute our value since we have obtained the unit. K is going to be equals to power is watts. Then lambda, which is our wavelength, is its own unit is meter, but we have squared in the equation as meter square, over current is ampere, but then square in its equation as well. Then length is meter square. So in that case, we are going to have meter square cancel meter square. So the value for K becomes watts per ampere square. Watts per ampere square, which we can also write as watts A raised power minus 2. Here we have applied the second application that says determination of units and dimension of constants. Now let's move to the next example. As you can see on the screen, this example says that Bernoulli's equation, which applies to fluid, states that P plus half density V square plus density GH equals to constant, where P is pressure, H is height, rho is density, G acceleration due to gravity, V velocity, and K a constant. Show that the equation is dimensionally consistent and state an SI unit for K. Want to check maybe the equation is dimensionally consistent? Let's rewrite our equation that says that P plus 1 over 2 density V square plus density GH is equals to constant. What are we supposed to do? We want to check maybe the dimension of P will be the same as dimension of density V square, be the same as dimension of density GH. If they are the same, that means the equation is dimensionally consistent. So let's start by checking the dimension of P. Say A part. Dimension of P we know square bracket represents dimension. Now, from the definition of pressure as force over area, the dimension of force is mLT raised power minus 2, while the dimension of area is L square. So we are going to substitute into this equation to have pressure is going to be equals to, in place of force, we write mLT raised power minus 2 over L square. Now, since we only have one L, we cancel out, this one will be left with one L, and we are going to be obtaining pressure to be equals to M. And the L is the denominator side, it goes on, becomes L raised power minus 1, T raised power minus 2. Therefore, the dimension of pressure is equal to M L minus 1, T raised power minus 2. So we have obtained the dimension of pressure. Let's look at the dimension of density V square. I'm going to check out the dimension of density V square. We can write the equation this way. Now, what is the dimension of density? If we remember that density is mass over volume, so its dimension, it's going to be mass is capital letter M, while volume is L cube. So here the density dimension is going to be M raised power minus 3. So we can solve it this way. The dimension of density is now M raised power minus 3 times dimension of velocity is LT raised power minus 1, but we have square of it. So we are going to have M raised power minus 3. If you apply law of indices, this square is for both L and T, and the power here is 1. So 1 times 2 will give us L squared, then T raised power minus 2. So we are going to obtain M. We have 2L. We can solve it by saying L raised power minus 3 multiplied by L raised power 2, and that will give us pick one of the L. The first power is minus 3. Multiplication in indices means plus, and we have 2, and that will give us L raised power minus 1. So here we are going to have L raised power minus 1. We only have one T, that is T raised power minus 2. So the dimension, as you can see, the dimension of density V square, which is this, is the same as dimension of M of pressure, which is ML minus 1, T minus 2. So we are left with the third part, the third term of the equation, which we have to look at it from here. That says density GH. Now let's look at density GH. Density GH dimension. How are we going to do this? That means we can rewrite it by saying density dimension multiplied by acceleration due to gravity dimension multiplied by height dimension. So that means we need to check out for the dimension of density G and height. The dimension of density, we know it to be ml raised power minus 3, while dimension of acceleration due to gravity is LT raised power minus 2, the same as acceleration. Then the dimension of height is L. Now we can substitute it into the equation by saying dimension of density GH is going to be dimension of density is ml raised power minus 3 multiplied by dimension of acceleration gravity raised power minus 2 multiplied by height, that's L. So if we want to solve this, we only have a single M rather. So we write M, but we have L to be 3 places. That's to say L raised power minus 3 multiplied by L multiplied by L, and that should be giving us S power minus 1. We try to use indices to solve it. L power minus 1, then we have single T, that gives us T raised power minus 2. So here the dimension of density GH is given as this, which is the same as dimension of density V square, also the same as dimension of the previous one, density of pressure rather. So since the three parameters, what are the three parameters? The three parameters that we say P plus 1 over 2 density V square plus density GH. They all have the same dimension, hence we can conclude that this equation is dimensionally consistent. Now, the B part of the question says that we should solve for the dimension of K. We are going to use the principle of dimensional homogeneity that says that if we have A plus B is equals to C plus D, if this equation is going to be dimensionally consistent, that means these parameters A, B, C, and D, they will have the same unit and dimension. And we already confirmed that pressure has the same unit as density V square, has the same unit as density GH. Therefore, we can say that the unit and dimension of P is same as K. The unit and dimension of density V square is the same as K, and unit and dimension of density GH is the same as K. In that case, we can just say K is equal to pressure, or I can also use the second part of the equation that K is equals to density V square, or K is equals to density GH. But it's easier to use this. Now, we want to get the unit. We start from pressure. Pressure is force over area. So in this case, I can decide to use the derived unit for force, which is Newton, and the unit for area is meter square. So pressure becomes Newton per meter square, which is otherwise known as Pascal. So in this way, if the unit of pressure is Pascal or Newton per meter square, therefore the unit of K is also going to be Newton per meter square or Pascal, and K will also have the same dimension as pressure and other parts of the equation. K will have the same unit and dimension of pressure, which is ms per minus 1 T raised per minus 2. So this is all about the third example. Let's look at the fifth example. Here, the question says that the heat, capital letter H, produced in a wire carrying an electric current depends on the current I, the resistance R, and the time T. Assuming that the dependence is related by the equation, use dimension analysis to determine the values of X, Y, and Z. Also, find the expression for H. To solve this, we are going to be making use of the last application that says that establishment or derivation of an equation. Now, we have the statements given in mathematical form as H depends on current, X, R depends on Y, and T, Z. So the next thing is to remove the proportional sign and write it like this. H is equals to K I X R of Y C Z. We call this one equation 1. Now, they say we should use dimensional analysis. Is either we make use of base unit method or we use dimension method to solve this question. Let's say we want to make use of dimension method. That means we need to obtain the dimensions of the dependent and independent variables. So the independent variables are on the right hand side. We have discussed that while the dependent variable is on the left hand side, which is H. So what is the dimension of heat energy? Heat energy, just like other forms of energy such as mechanical energy, electrical energy, we have our solar energy, they are mostly expressed in joules. That's the unit. But we are talking about the dimension, so that is just like other energy, which is mL squared T raised per minus 2. Now, the dimension of current is A, while the dimension of time is written as capital letter T. What is the dimension of resistance? That means we need to work out the dimension of resistance since we did not remember that. So how do we work it out? We start from Ohm's law. Let's work it out somewhere first. We start from Ohm's law that says R is equals to V over I. Now, what is the dimension of voltage? We can get dimension of voltage from work done over charge, and that will give us work done is just ml squared t raised power minus 2 over charge. Charge is 80 from current times time, so voltage is going to be equals to ml squared a raised power minus 1 t raised power minus 3. Now we can use the dimension of voltage to obtain that of resistance. So to get resistance, R is going to be equal to V is given as ml square a minus 1 t minus 3 over current. Current is A. Here resistance becomes ml square. When this A goes up, becomes a raised power minus 2 t raised power minus 3, and this represents the dimension of resistance. Now that I've gotten dimension of resistance, we can return it back into the equation 1 that says that let's turn it back to equation 1. That means in place of this H, we are going to be writing ml square t minus 2. We can ignore the k since it is a constant for now. We can ignore it. Then current, its own dimension is A. Then we have X. Y resistance, we have ml square a minus 2 t minus 3 raised power y. Then t dimension is capital letter T raised power z. Now with this, we can open the bracket by saying ml square t minus 2 is equals to ax, open the bracket, that gives us m raised power y, l raised power 2y, a raised power minus 2y, then t raised power minus 3y. We're left with tz. Now let's rearrange very well. That gives us ml square t minus 2 is equals to, let me write m first, that gives us m y. We can write l next as l raised power 2y. The arrangement doesn't really matter, we can arrange it anyhow. L raised power 2y followed by a, we have a raised power x, and we have a raised power minus 2y. Then we have t raised power minus 3y, and we have t raised power z. Since we have this, the next thing is to perform indices. ml square t raised power minus 2 will give us m raised power y, l raised power 2y. Then we have ax, x plus minus 2y will give us minus 2y. Then t raised power minus 3y plus this will give us minus 3y plus z. With this, we can compare both sides of the equation. But before we compare both sides of the equation, we have to check that on the left hand side, on the right hand side, we have some parameters here, and we have some. Here we have mlat, here we have mlt. That means a is missing. We can as well bring it in by raising it to the power of 0, because raising to the power of 0 will still make it 1, and we get the original value back. So in this case, we can apply principle of dimensional homogeneity that says that if an equation is dimensionally correct, that means the left hand side must be equals to the right hand side. And in that case, we can start comparing the terms. Let's start by looking at A. Let's compare A on both sides of the equation. That means A on the left hand side is raised power 0, then A on the right hand side is raised power x minus 2y. In this A, we cancel A, then we'll be left with x minus 2y is equals to 0, equation 2. Then let's look at the next one. Let's compare the value for m. Let's compare m on both sides. On the left hand side, we have m raised power 1. Then on the right hand side, we have m raised power y. So in this case, if we try to cancel it, we are going to be having, that means m cancel m. We have cancelled it because they have the same base according to law of indices. That means y is equals to 1. We have gotten that. Then let's look at compare L on both sides. L on the left hand side, we have L is power 2. L is power 2. L on the right hand side, we have L is power 2y. In this case, if we try to cancel it, L cancel L because they have the same base, and we are going to be having 2y is equals to 2, and in that case y becomes 1 as well, which is still the same as the one that we did from M. That means y is correct. Let's compare the t that we have on both sides. We have t raised power minus 2 on the left hand side, then we have t raised power minus 3y plus z. So in that case, we can as well cancel it by saying t cancel t because of the fact that they have the same base. Then we are going to be having minus 3y plus z is equals to minus 2. We can call this one equation 3. If that be the case, we have gotten the value of y, so we can substitute to equation 3 so as to get the value of x, of z rather. That will give us minus 3 into bracket of 1 plus z equals to minus 2. In that case, we are going to be having minus 3 plus z equals to minus 2. So we can transfer minus 3 to the other side. So z becomes minus 2 plus 3, and that gives us 1. So we have gotten the values of y and z. Let's use that to get the value for x. From equation 2, we have x minus 2y equals to 0. As equation 2, that says x minus 2y is equals to 0. Equation 2. So the value for y is 1. That means we have x minus 2 into bracket of 1 give us 0. So we have x minus, open the bracket, and give us minus 2 equals to 0. Transfer the minus 2 to the other side, x becomes what? 2. Now we have gotten the three values. That is, the values of x is equals to 2, the value for y is equals to 1, while the value for z is equals to 1. That's the first part of the question. The other part of the question says that we should look for an equation for h. You see, from this expression that says h is equals to k I raised power x r raised power y c raised power z. That's equation 1 that we discussed the other time. So in that case, let's substitute our value. That means h is going to be equals to k I, the value for x is 2, the value for y is 1, and the value for z is also 1. So if we simplify further, h is going to be equals to k I square rt. Now we take k to be equals to 1, so h is going to be equals to I square rt, and this is the solution to the question stated above. So we have solved the example 5 question. Let's look at the last question on dimensional analysis. Let's take a look at the last example, which is example 6, which says that the van der Waals equation for real gases is given by P plus AN square over V square into bracket V minus NB equals to nRT, where A and B are dimensional constant. P, V, T have their usual meanings, and N equals to number of mole, and R is universal gas constant in joules per mole per Kelvin. Derive the possible units and dimensions for van der Waals constants A and B. So how do we solve this? Let's write the equation first. We are going to be using principle of dimensional homogeneity as well. Now let's look at this equation at see this represents x. Everything here, let's take a look at it as represents x, while everything here represents y. Everything here, let's say it represents z. So I can just say that x, y is equals to z. That means the left hand side, which is xy, must be equals to the right hand side, which is what? Z. That simply means P plus AN squared V squared their dimensions, if I multiply it with the dimension of V minus MB, is going to give us nRT. We are still applying principle of dimensional homogeneity. The dimension of P plus N squared over V squared, like I've said, when we multiply with V minus MB, it must give us nRT dimension. That is what principle of dimensional homogeneity is trying to say. That means here, let's start with A part. That's to say P plus AN squared over V squared. We have the same unit and dimension. That means P, we have the same unit and dimension as AN squared over V squared. That is, we're going to write as dimension of P is same thing as dimension of AN squared over V squared. Therefore, you can say that P is equals to AN squared over V squared. They are going to have the same dimensional unit. Now, we are going to use the application that says the dimension of units and dimension of constants. Here, the constant involved is A. These are constants involved, it is A. So in that case, we have to make A the subject of the formula. How do we go about that? That means I will cross multiply this. I'll be having P V squared equals to AN squared. Then make A on the side that we have here, this side, N squared is still attached to A, so we have to remove N squared by saying by dividing both sides by N squared. So A is going to be equals to PV squared over N squared. That's equation 3. With this, we can solve for the unit and dimension of A. Let's start by looking at the unit of A. The unit of P is Newton per meter square. The unit of volume is meter cube, while the unit of number of mole is mole, which we have discussed in other video. So in this case, we can solve for A by saying pressure is Newton per meter square, while volume is meter cube, but we have square of it. In that case, we have over N is mole, but we have square of it as well. So that gives us Newton per meter square. If I simplify this by applying X, M, everything of N, I can as well write it as X power M times N. So we try to use that principle. Here we are going to be multiplying 3 times 2. That gives us M raised power 6 over mole squared. So if I use indices to solve this, we are going to be having Newton. The pick one of the M. The first power is minus 2, while the second power is plus 6. So over mole squared. So the value for A becomes Newton meter raised power 4 over mole square, and that we can simply write the unit as Newton meter raised power 4 M raised power minus 2. What is the unit of A? Let's look at the dimension of A as well. The dimension of A, we are still going to use the equation that we derived for A, that says that A is equals to PV square over N square. That is the equation that we derive for A. So if that be the case, that's equation 3. If that be the case, the dimension of pressure is ML minus 1 T minus 2, and dimension of volume is given as L cube. While the dimension for number of mole, we can take it as 1. I'm going to take it as 1 in this case, or I can as well use it as capital letter N, which represents the original unit. So in this case, we are going to be working with 1. So our value becomes P is ML raised power minus 1, T raised power minus 2, multiplied by V square. Our value for V square volume is L cube, but we have square of it over n, which is taken as 1 square. So in that case, we'll be having n raised power minus 1, c raised power minus 2. If we open the brackets, we are going to be having L raised power 5. So the dimension of A, which is a dimensional constant, is going to be equal to n we solve for a minus 1 plus 6, rather, this is 6, minus 1 plus 6 will give us 5. Then we are left with 3 raised power minus 2. This is the dimension of A. Now let's look at the constant B. We also said that V minus B is this other part of the equation. Now, if the equation is dimensionally correct, that means the dimension of V is same as the dimension of NB, and in that case, we can write it as V is equals to NB. Let's take this as equation 4. Now, if that be the case, let's solve for the unit and the dimension as well. Before that, that means to solve for the units, we need to make the B the subject of the formula by saying B is equals to V over N. We can say that's equation 5. So for the units, B is going to be equals to volume is meter cube, while number of mole is mole. So we can just say that meter cube per mole. That is the dimension. The unit of B, rather. Let's solve for the dimension as well. Dimension of the constants, we are going to be having it this way. B dimension is going to be equals to volume is L cube. Here we can take the dimension of number of moles to be 1. If you don't want to take it as 1, you can include it by using N, and that we also need to adjust the dimension of A, which is the other constant. In this case, we are having it as L cube. So we have solved for the unit and dimension of the constants involved. I want you to feel free to try solving for the dimension of the constant that we have. We still have a constant called universal gas constant. So try to solve for the unit and dimension of this constant by using the principle of dimensional homogeneity, and let me know your answer through the comment section. Thank you.